Operational amplifiers or op amps in short are analog amplifiers. They belong to the category of direct coupled amplifiers. They are voltage amplifiers capable of providing very high voltage gains. They are considered to be the most versatile amplifiers. They take two inputs. They give a single output. Input side, there exists two terminals. One terminal is called inverting terminal. The other terminal is labeled as non-inverting terminal. As already mentioned, only one terminal exists on the output side. Inside, the structure can be divided into three parts. First part or the front end part is a differential amplifier. Second part is one which provides gain, high gain. Third part is one which acts as a source or a sink. Out of these three, first one plays major role in the functioning of operational amplifier. It is this stage which decides the performance of the operational amplifier. There are several applications for operational amplifiers. In earlier days, it is the one that is widely used in a maximum number of applications. It is the mainstay in implementing the process control in industries. Academically, its applications include implementation of operations, mathematical operations like addition, subtraction, scaling, phase shifting, integration, differentiation, and many more such operations. Its specialty is performing operations, mathematical operations. Hence, the term operational in its name. Ideal operational amplifier is supposed to have infinite input impedance, zero output impedance, infinite voltage gain, infinite bandwidth, perfect balance. But these are all characteristics of an ideal amplifier. In reality, they are not available from the amplifier circuit. Input resistance is not infinity, but it is high. Output resistance is not zero, but it is low. Gain is not infinity, but it is high. Hence, in practical operational amplifiers, ideal qualities are not found, but depending upon the quality of design, the practical op amp tries to perform as near to as possible to an ideal op amp. Amplifiers, operational amplifiers, part 2, series on semiconductor devices and circuits, lecture number 8.17. Op amps are analog amplifiers. They are direct coupled amplifiers. They are high gain amplifiers. They are considered as versatile. They are capable of performing so many mathematical operations, including addition, subtraction, integration, differentiation, etc. This is second part of the session on op amps. In this part, we focus on how op amp is able to perform operations, mathematical operations. Let us start with the inverting mode of op amp. Op amp is called op amp because it can be used to perform operations, mathematical operations. It is capable of performing mathematical operations. Hence the name operational amplifier. In case of inverting configuration, the voltage gain is V0 by Vs. V0 is output voltage, Vs is source voltage. It is Z prime by Z with minus sign. This is the relation based on which one can obtain an analog inverter, sign changer, scale changer, phase shifter, adder, integrator, differentiator, etc. Hence, one has to keep in mind that inverting configuration of op amp is the one that has the capability of performing operations, mathematical operations, and the basic relation underlying the performance of all these operations is this one. AVF is minus Z prime by Z. It is also possible to construct a voltage to current converter, current to voltage converter, DC voltage follower, etc. Several other operations. In fact, innumerable operations, innumerable applications are there for op amps. Now we spend some time on applications of op amp when it is functioning in inverting mode. Inverter or sign changer. This can be designed by op amp with it in inverting mode. If Z is Z prime, then AVF becomes minus 1 and the sign of the signal changes. AVF means output by input, that is V0 by Vs. When V0 by Vs is minus 1, it implies V0 is equal to Vs magnitude wise, but sign is different. In such case, the circuit is called inverter or sign changer. Hence, such a circuit can act as a phase inverter. A cascade of two such amplifiers is called paraphrase amplifier. So the output of a paraphrase amplifier is same as its input. Another application of op amp is as a scale changer. If Z prime by Z is K, the real constant, then AVF becomes minus K. And the scale has been multiplied by a factor minus K. Signal, instead of scale, it should be signal. The signal has been multiplied by a factor minus K. Another use is as a phase shifter. If Z and Z prime are equal in magnitude but differ in angle, then Op amp shifts the phase of sinusoidal input voltage while at the same time preserving the amplitude. A phase shift by any amount in between 0 to 360 degrees can be obtained. So it can be used as an inverter, it can be used as a scale changer, it can be used even as a phase shifter by selecting Z prime and Z properly. Now, in addition to the operations that are mentioned in the previous slide, another operation can also be performed by inverting op amp, that is addition. It can act as adder. The circuit is being shown here. This is op amp. Here is R prime, R1, R2, etc. Rn. Several resistors are there. Notice all these resistors are connected to inverting terminal. Each resistor is given an input V1, V2, etc. Vn. Output is V0. This is the circuit with which one can do addition. The mathematical foundation behind this circuit, it will be shown in the next slide. Now, it is possible to obtain an output which is a linear combination of a number of input signals with a ladder of input resistors. V0 is equal to minus R prime V1 by R1 plus V2 by R2 plus Vn by Rn. This is the output voltage for the circuit that is shown in the previous slide. When R1 equal to R2 equal to R3 equal to Rn, then output voltage becomes equal to minus R prime by R1, V1 plus V2 plus etc. plus Vn. So output is being added inputs of the circuit. Of course, when we choose R prime by R1 as 1, V0 is simply the addition of inputs to the circuit. Op amp can also perform integration and differentiation. First, we consider integration operation. If Z equal to R, here R is a resistor and a capacitor C is in place of Z prime, then V0 becomes equal to minus 1 by RC integral Vi dt. It can also do differentiation. How? If a capacitor C is in place of Z and Z prime is R, a resistor, then V0 is minus RC dBi by dt. It can also be used in the design of a logarithmic amplifier and also an exponential amplifier. If Z equal to R and a diode D is in feedback loop in place of Z prime, then V0 is equal to minus Vt natural logarithm Vi by ISR plus 1. So this is logarithmic amplification. Exponential amplifier. If a diode D is in place of Z and Z prime is R, then V0 is minus ISR exponential Vi by Vt plus 1. In the earlier case, Vi is inside logarithm. In the present case, Vi is inside exponential. That's why it is exponential amplifier. Previous one is logarithmic amplifier. Here Vt is volt equivalent of temperature, T by 11,600. It can be used op amp in inverting mode, can be used as voltage to current converter. The circuit is shown in A. and also it is being shown in B with a slight modification. In A, load is a floating load. In B, load is grounded load. Load is ZL. It is grounded in B. That's why a grounded load circuit. In A, here is ZL. It is floating. So these two circuits, they are meant for converting voltage into current. A few points regarding voltage to current conversion. It is desirable to convert a voltage signal to a proportional output current. For example, when we drive a deflection coil in a television tube, if the load is grounded on either side, the circuit A, if the load is not grounded on either side, the circuit A can be used for conversion. In this circuit, very little current from the signal source is drawn due to very large input resistance seen by non-inverting terminal. If the load is grounded, as in B, we can show that if with R3 by R2 equal to R prime by R1, IL is load current is equal to minus Vs of t by R2. So current in the load, it is proportional to voltage of the source. So voltage is being converted into load current. Voltage is being transformed into proportional current. It can also be used to convert current into voltage. The circuit is shown here. This is current source. This configuration is able to provide a voltage which is proportional to current. So current is being converted into voltage. A few points regarding to current to voltage conversion. Photocells and photomultipliers tubes give an output current which is independent of load. It is desirable to convert their output current into a proportional voltage, which can be done with an op amp circuit. The output voltage V0 of the amplifier for input current Is is given by this formula. V0 is equal to Is R prime. What does it mean? Input is this. It is a current. Is is current. Output is voltage. Output voltage is proportional to input current. Here one can see clearly current being transformed into voltage, current being converted into proportional voltage. So far, whatever we discussed, they are all concerned with inverting op amp. Now, a few points regarding non-inverting op amp. Here is shown a non-inverting op amp with resistive feedback. This is feedback. Source is connected here, Vs. The source is terminated on non-inverting terminal. This is output. The inverting terminal is grounded through a resistor R. So this is a typical non-inverting op amp configuration. Some important points regarding non-inverting op amp. It is an amplifier whose output is equal to and in phase with the input. Notice, in case of inverting op amp, output is out of phase with the input, but here it is in phase. Its input resistance tends to infinity, output resistance tends to 0, so that in effect the load and source are isolated. It uses non-inverting terminal for signals and an inverting terminal for the feedback voltage. Its closed loop voltage gain is given by this formula, R plus R prime by R. Notice that this is different from voltage gain of inverting op amp. Now we discuss certain limitations of a practical op amps. Ideal op amp is supposed to have infinite input resistance, zero output resistance. As already mentioned, infinite resistance is not achievable in practice. High resistance can be achieved. Similarly, zero resistance cannot be achieved in practice. Small resistance can be achieved. So practical amplifiers do not exhibit ideal characteristics. Practical amplifiers are always associated with certain limitations. Those limitations pertaining to op amps, some of them are considered here right now. CMRR is a ratio of differential mode gain to common mode gain. CMRR stands for common mode rejection ratio. For ideal amplifier, it should be infinite, but in practice, it is a finite value, typically 80 to 100 dB. The voltage that is generated due to device mismatch in the input stage is called input offset voltage. It leads to latch up or saturation problem. So this is another limitation. The mismatch between the input devices cause a mismatch between input base currents in BJT op amp. The difference of these currents is called input offset current. So existence of input offset voltage, input offset current, these are issues. These are problems one can find in practical real life amplifiers. These are not present in ideal amplifier. Some more limitations. Saturation voltages. In real op amp, the output voltage swing is less than maximum possible with unequal positive and negative swings. It leads to clipping and distortion of the output unless input signal is limited to small. This is another limitation. Unless it is properly addressed, unless it is taken into account in the design, it results in clipping and distortion. Minimum allowed supply voltage. The supply voltage should be more than a certain value that is required to keep all the transistors. More than certain value that is required to keep all the transistors in the branches of the circuit in forward active mode. During large-scale operation, compensation capacitor comes into play, limiting slew rate. The maximum angular frequency of the input signal is given by this formula. Omega m is SR means slew rate by V sat. This is also referred as a full power bandwidth. Omega is full power bandwidth. It is equal to SR slew rate by V sat. With this, we come to an end of this session. Second part on op amps. In this part, the focus is on inverting op amp configurations that are capable of performing mathematical operations. At the end, we also discussed non-inverting op amp and limitations of op amps in general. Hope this part as well as the total session is useful to you. We meet again in another session with a new topic soon.